Hi there. For this last lecture about gene expression, I want to talk about a subject that gets, I think, a little less press than it really should, because multiple testing correction is one of the most essential things to understand in making sense of systems biology data, and gene expression data certainly count. So without further ado, let's move ahead. The first question I want to address is, why is this necessary? Understanding why it is that performing more difference tests will always yield more hits is a difficult thing for a lot of people to get their heads wrapped around. So I hope we can start addressing that question. From there, we're going to talk about two methods. One is the Bonferroni Correction. It was created by a woman who was an American statistician to protect against any false positives, to prevent us from thinking any genes are differential if they are not truly so. The next is the Benjamini-Hochberg Correction. This is an effort to limit the proportion of false positives. So these are different kinds of goals, and they apply under different circumstances. But let's go ahead to talk about this important topic step by step. So first off, why do we need multiple testing correction? We looked at this table in the previous set of slides. We were talking about difference testing there, but now I want you to think about this from a statistical point of view. We said that we were going to consider the data for each gene separately. We were going to evaluate whether this gene is differential based on its expression alone, not on the rest of the table. As a result, each of the rows in this table comprises a different statistical test. That means that if you have 1,000 genes that you're measuring expression for, you have 1,000 statistical tests. The next problem that we need to understand is that we can detect differences even when none of them exist. So a t-test, student's t-test, yields a p-value below 0.05 for 1 in 20 tests when no difference exists. It's an important concept. You might think that if you run t-test in a bunch of data that are from the same mean and the same distribution, so A and B distributions overlap right on each other, that it would never give you a p-value below 0.05. But that is not correct. When t-test gives you a p-value below at 0.05, it's saying that 1 in 20 times we would expect by random chance to get a t-statistic more extreme than this. So, its declaration is not to say, yes, I validate that a difference exists. Instead, it is saying how likely it is that if there were no difference, a t-statistic that extreme would come about. So that's already a bit of a shock for some folks. So if you do 20 t-tests on data that are no different whatsoever, you should get one p-value that's below 0.05 just by random chance alone. Important. Okay, now that happens because when you have random data that are drawn from the same distribution, they're normally distributed, they have the same mean, the same standard deviation, the p-values that come out of those tests should be uniformly distributed, meaning that there's just as many values between 0 and 0.5 as there are between 0.05 and 0.1, as there are between 0.1 and 0.15, etc. That's uniform distribution. So if you have 1,000 different genes, each of which has gene expression data, you should expect that 50 of them will be significant differences by random chance alone if you use a threshold of p less than 0.05, because 0.05 times 1,000 is 50. So how do we protect against this? There have been these two different approaches, and these are just two very, very popular ones. They are not the only options by any chance. The first of these is an approach that you may have seen in the context of GWAS, G-W-A-S, Genome-Wide Association Studies. And frequently, we see a Bonferroni correction used in connection with Manhattan plots. We have some list of genes, and we ask which of these SNPs, rather, is significantly associated with this phenotype. So for that, we use something very like Bonferroni correction. Bonferroni is trying to protect you from making any errors at all, from having any false positives, sorry, not any errors, but any false positives per se. So we want to protect ourselves from claiming any gene is differential in between these two cohorts. If you want to protect yourself at that level, you need to divide the threshold you would normally use, for example 0.05, divide that by the number of genes that you're going to be comparing. So if you have 5,000 genes or 20,000 genes on your array, this may mean that the new threshold for a significant p-value is vanishingly small. That's really hard to beat. So Bonferroni is not that frequently used when we have data of when we have relatively few samples to work from. So a lot of people opt instead for what's called false discovery rate, or Benjamini-Hochberg correction. And the goal of Benjamini-Hochberg is not to protect you from making any false positives, but rather to control the rate of false positives. So imagine that you're willing to have up to 5% errors among a set of genes that are called differential. That would mean that if your study found 20 genes were differential between these cohorts, one of those would be a wrong call. Most people are willing to accept that level of error. So under those circumstances, we're going to start by sorting all of the genes by whatever p-values have been associated with them. And we're now going to sort them from the lowest value up to the highest value. Now, each of these genes in succession is going to get a higher threshold applied to it. So over time, we're going to find that the thresholds are rising at a rate slower than the p-values are escalating. And you can see an example in the diagram that we show at the lower right. This red line reflects the rising threshold, and we see that the data points themselves eventually rise above that line. And that's the point at which we no longer allow any more onto our list, that we say this is the set of differences we're going to call significant. Sometimes you will also see that the p-values get transformed into values that you can use your 0.05 threshold against. Sometimes those are called Q values. So if you see that your statistical test is able to correct itself you're able to correct this array of p-values into an array of Q values, that's one indication that what you're getting is a false discovery rate, or Benjamini-Hochberg corrected set of p-values. Now, there are a lot of complaints in association with multiple testing correction, and I want to walk through them because you're going to hear these from people you work with from time to time. First off, the most common one is, all my hits vanished when I use multiple testing correction, so I can't use it. Well, I want you to hold your ground on this one. Remember that sometimes the null distribution is correct, which is to say that sometimes PIs make mistakes. Professors make mistakes, and they send you on a long series of experiments that only show there's no difference between knockouts and wild types for this particular phenotype. This happens. So sometimes the null distribution is correct, and there really is no biological difference to be measured. But very frequently, we're working with experiments that are underpowered. This might mean, for example, that you're comparing a triplicate set for this cohort versus a triplicate set for this cohort. And there's so much variability in the measurement that you can't find a really low p-value for any of the genes. In a case like this, we are underpowered. We don't have enough N. We don't have enough elements in this cohort to compare to this cohort in order to get a very low p-value. As a result, the hits vanish because they're not hits by the standards of this experiment. The next thing is a difficult statement for people to hear, but one that they need to hear nonetheless. Sometimes a person with a very, very big name in the field writes a paper in which they do not use multiple testing correction. And they get away with it because the reviewers say, well, somebody as famous as Dr. X could not possibly be making a mistake. Well, the reality is that people publish very questionable statistics all the time. You, as a very junior person, may not get the same kind of leeway from your reviewers as Dr. X gets. That is not fair, but that's the reality. People who are at more junior stages of their careers face greater scrutiny when they try to publish work than people who are very senior. So, all I can ask you here is don't become one of these people who's very famous, who publishes nonsense. It happens far too much in the biotechnology literature. Now, I'm going to talk about another way that multiple testing correction can sneak up on you. Imagine that you did 5 groups, groups A, B, C, D, and E, and now I compare each pair of groups, A's versus B's, A's versus C's, A's versus D's, etc. This is a lot of comparisons. In this case, I would have done 10 pairwise comparisons. B versus C, B versus D. It's a huge number of comparisons. In this case, even if I'm comparing on a single trait, I still walk myself into a multiple testing correction problem. So one of the things to do in a case like this is to remember that if you get into one of these, I must do this test and then that test and then this other test, you might remember that there are tests that exist for this purpose, like ANOVA. ANOVA is designed to handle tests where one factor can appear at 5 different levels, and it can protect you against multiple testing correction. Performing your experiment took caution. Analyzing it well also requires caution. I want to bring the words of Rundlecosa to you because he, I think, made a very apt expression about this. If you torture the data long enough, it will confess. Doing the statistics right does not mean you got a p-value below 0.05. Doing the statistics right means you understand the requirements of the test and it is appropriate to the circumstance in which you use it. You do not decide after the fact that the test must be the wrong one because it didn't give you a significant p-value. That is a very hard lesson to learn, and a lot of people really struggle to come to grips with it. So sometimes the experiment is at fault, not the statistics that are used to analyze them. There are a lot of takeaway messages here. Multiple testing correction is necessary because testing X hypotheses leads to X divided by 20 false positives, where the p-value is less than 0.05, even when the data have the same mean and variance. That is difficult. So just producing lots of tests should give you 1 in 20 times a p-value below 0.05. Many biological experiments allow for some fraction of error. In this case, using the Benjamini-Hochberg False Discovery Rate correction is acceptable. I hope you'll find that a useful overview of multiple testing correction, and that you can make use of this in lots of different contexts, not just in gene expression. Thank you very much for watching this series.